Good morning students, this is Junita Mukherjee once again in SS Public School giving you the notes of this particular chapter kinetic energy, making you learn this chapter kinetic theorem and kinetic interpretation of temperature we will discuss today. So from the pressure of an ideal gas we get this equation from this pressure of this ideal gas, that is we have this equation as P equal to 1 by 3 nm square bar. Okay, so we have taken this thing as 1 by 3 nv square to the power v square to bar from this particular equation, and we have taken this equation as equation number 1. Then we have pv is equal to 2 by 3 n x to the power 1 by 2 is equal to x to the power 1 by 2 nv square bar, and n will be equal to small n, and nv is the number of the moles in the sample itself. So n e will be equal to n into 1 by 2 nv square. Substitute this particular equation in this equation number 2. Then we will give this equation as 2b pv is equal to 2 by 3e. We can write like this. Now combining equation 4 with the ideal gas equation v square x square z square is equal to 1 by 3 vx square plus vy square plus vy z bar to the power bar is there, and 1 by 3 v2 bar is already given in this. So we can take this equation as e equal to 1 by 3 by 2 kb nt, where e born n is equal to 1 by 3 and v square is equal to 3 by 2 kb t. Fifth equation we have taken like this, and thus this equation 12 that is we have this from this equation number equation of the ideal gas equation. From this particular equation we will get this equation, and thus the average kinetic energy of a molecule is proportional to the absolute temperature of the gas. It is independent of pressure, volume or nature of the ideal gas. This is a fundamental result relating temperature, a macroscopic measurable parameter of a gas in thermodynamic variable, as it is called, to a molecular quantity, namely the average kinetic energy of a molecule. The two domains are connected by the Boltzmann constant. We know that in passing the equation number 3.18, that is E equal to 3 by 2 kb nt. We have already here written this particular equation. So this particular equation is equals to kb nt, which we have written as A. This particular equation will be written as A equal to this, and from this equation we will tell that the internal energy of the ideal gas depends on the temperature, not on the pressure or the volume. So it is depending on the temperature of the ideal gas equation, not on pressure and volume. And the interpretation of the temperature, that is kinetic theory of an ideal gas, is completely consistent with the ideal gas equation and various gas laws based on it. For the mixture of the non-reactive ideal gases, the total pressure contributed from each gases in the mixture is given by the equation P equal to 1 by 3 n1 m1 v1 square plus n2 v2 m2 v2 the v2 bar v2 square bar plus and so on will be equal to 1 by m1 v1 square is equal to 1 by 2 m2 v2 square is equal to 3 by 2 kb2 kbt we have taken. So we will take this equation as this, so that P equal to n1 n2 n3 and so on kbt. So in the equation we can take like this. Okay, now this is what we call the Dalton's law of partial pressure. From the equation number this thing, that is E upon n, this fifth equation. Okay, from this fifth equation, that is we can get the idea of the typical speed of a molecule in a gas at a temperature T equal to 300 Kelvin. The mean square speed of a molecule in nitrogen gas is m equal to n2 is equal to 28 upon 6.02 into 10 power 26, that will be equal to 4.65 into 10 power 26 kgs. Okay, so we will have this v square bar will be equal to 3 kbt upon m, that will be equal to 516 meter per second square, and this particular value will be the root mean square. V square is known as the root mean square velocity and is denoted by v square, and thus we can have this value as this. Okay, now we can write that v square, the speed of the order of the speed of the sound in air. It follows that equation number this particular equation this particular equation, that is equation number 5, is the same for the temperature, and at the same temperature lighter molecules have greater RMS speed. So lighter molecules, which have the lighter molecules, they have the root mean square velocity larger in comparison to the other values of the heavier molecules. So this particular thing is being given to you, that is in the kinetic interpretation of temperature. It is depending on the temperature, not on the partial units of pressure or the volume itself. It is depending on the temperature itself, and how it is depending we have already been seen. And the temperature at 310 degrees Kelvin is being shown, and thus the RMS value has been calculated by this particular value, and NA value is given by this particular value, and N2 is given by 28 values. The 28 is the value of this, and thus we will calculate, we have interpreted the temperature in the kinetic theory itself. Now we will move on to the next theorem thing, that is law of equipartition of energy. In this law of equipartition of energy, we will discuss the law of equipartition, law of the kinetic energy of a single molecule, how it has been written, and how the direction has been implied. No preferred direction has been taken. And all the directions have the same value, that is x, y and z will have the same values in this law of equipartition of energy, because law of equipartition means equally division partition of energy in all the values or all the different dimensions. So let us do this particular topic in the next series, next video. Till then, take care, and please read the topics and comment in the comment section if you have some problem.